Good morning, everyone. Happy Monday. And today it will be the last class with material to be examined on the exam. And in some sense, we complete the material of the syllabus for the semester. We might add a few more things, as you're going to see, especially in terms of other differential equations. But today we would like to bring it all together and do an example of the heat equation and Fourier analysis. So let me remind you what we have done so far and how the two things that we did in the past 3 lectures can now come together and give us the full solution of the problem. So we have been interested in the heat equation. Here we want x to be between 0 and L, and t to be greater than or equal to 0. So it's a problem of finding out how the heat is propagating on a rod. At least this is the basic model that this problem presents us with. And we have been studying the insulated case. As we're going to see later, it is possible to actually drop this condition or replace it with something else. And we also suppose that we know the initial distribution of heat on the rod. So if we would like to sketch what is known, then we would have the x-axis, and then we would have the t-axis, because x and t are two variables here. And we're interested in this problem on this domain. This is the domain over which the problem is defined. So x is between 0 and L, and t is greater than or equal to 0. And basically, what we're saying is that this condition right here tells us how to find these two parts, right? Tells us that these two parts are equal to 0. And this condition right here tells us how to find the values of the heat distribution function over this segment. And basically, the whole point of this problem is to eventually solve for it and find a function that represents the heat, the temperature, if you will, on in the interior of this one-sided strip. So we have solved this problem, and basically we said that u of x comma t is given by a function of this form. And here, what I would like you to remember, I mean, we did this in a lot of detail, is that this function right here satisfies the first two conditions, meaning the differential equation and the condition that gives us the insulation, that the problem is insulated. And of course, now, the final step in solving this problem is to choose the CNs so that the last condition is satisfied. So if you set t equal to 0, then the exponential component disappears, becomes 1. And pretty much what you get is that f of x should end up being the series starting with 1 to infinity of Cn sine of n pi over L times x. And at this point, at least theoretically speaking, because we haven't done a single example, we were able to argue that Cn should be 2 over L times the integral from 0 to L of f of x times sine of n pi over L times x dx. And the idea here is that this is based on the sine expansion of f of x on the interval from negative L to L, assuming that it has been expanded onto negative L to 0, because look, the function f of x is initially given where? In the range for x between 0 and L, right? And we know that the expansion that we wrote corresponds to a Fourier expansion on a larger interval, on the interval from negative L to L. And if you want to force this expansion to be a sine expansion, then you need to consider the odd extension, meaning the extension that forces the function to be an odd function, so as to be an odd function. Okay. Any questions, please? So this is the full theoretical picture. And as you can see, your book has 2 more problems, the wave equation and the Laplace equation. And you can see that there is a great general similarity with what we have done, but the problems themselves are different, certainly, because the equations are different. And also the boundary conditions are also different. So eventually you get the same pattern. What does that mean? That you create an you separate the variables, create an eigenvalue problem, you find the eigenvalues, you find the eigenfunctions, and then you apply Fourier analysis to the initial condition and make sure that you get a function that satisfies those conditions. So always the separation of variables step is going to produce functions that satisfy the homogeneous conditions that you had in this problem. And then, of course, you will need to apply Fourier analysis in order to also satisfy the initial condition. Okay, that's how it works. So so the part that we have not seen so far together is the part that we actually compute the Fourier coefficients of in a heat equation problem, and this is what I would like to do today. So are there any questions so far, please? And we should mention here that the theory of ordinary differential equations, the way we have seen it, contributes in two places in this long solution of the problem, where in finding the functions x and t that you put together when you create these functions right here. Okay, and in fact, you've seen that we're talking about homogeneous linear equations. You have one equation of the second order and one equation of the first order for this particular problem. So now here's what I would like to do. I would like to choose the function f of x appropriately so that we get an interesting problem that we can solve using this method. So I don't want f of x to be a finite linear combination of these sine functions, because then you don't need Fourier analysis in order to solve it. These are the types of problems that you have seen on your homework. And if you look at your homework assignment for next time, you will realize that this is the last homework assignment due on Wednesday, where we're going to have our quiz. And you will realize that I have given you just one problem. Okay. And this problem will be worth, 30 points. That's fine. It's just one assignment. And this will be the last assignment for the semester. The issue that we have here, the challenge that we face when we look at this kind of problems, is that we want to find a function f of x that is continuous on the one hand, and also satisfies f of 0 equals f of L equals 0. So if we want to have a meaningful problem that allows us to come up with an agreeable situation here, then we should look for a function that satisfies these conditions. Okay, so so here's the problem that I would like to solve today with you. And I would like to take this opportunity in order to pretty much repeat all the steps in detail and have this as a review of what we have done in the past few days, in the past few lectures. So I would like to consider the following problem. U sub t is equal to 3 times uxx. And x is between 0 and pi. T is greater than or equal to 0. U of 0 comma t is equal to u of pi comma t is equal to 0. And u of x comma 0. So now I need a function between 0 and pi, which is continuous. And for that reason, I will take pi x minus x squared. So why do I take the function this way? Because, you know, another small detail here, I want the function to actually be non-negative. Remember that intuitively speaking, u of x is a u of x comma t represents the temperature. And no, I mean, you know, I think what I'm saying is incorrect here because the temperature could be negative. Yeah, okay, but so it doesn't matter. Just drop this last thing that I was saying. I really want it to be continuous, and I really want it to be 0 at both endpoints. And this function accomplishes this. In fact, in terms of polynomials, that's the least degree that I could find that can do this. Why am I saying that? Because if you have a smaller degree, so if you had degree 1, that would give you a linear function. Unless it's equal to 0, there's no way to force it to be 0 at the two endpoints, right? Unless it's identically equal to 0. And of course, you know, that should not be the case here. Okay, so does anybody have any questions on the statement of the problem? And we will continue with the solution of this problem by using the method of separation of variables, showing all the steps, and finally doing the Fourier analysis over the integral, over the interval 0 to pi. Okay, so an opportunity from everybody to see all the steps from scratch for this particular problem. Okay, any questions? Okay, so let's solve this problem fully. Now, what did we say? We're looking for functions of the form u of x comma t that are going to consist of a quantity in x and a quantity in t that satisfying first two conditions of the problem, meaning the equation itself and the insulation condition. So if we do that and we plug it into the equation, then that will give us x of x times t prime, that's the partial derivative with respect to t, is equal to 3x double prime times t, right? And now what we do is the usual thing. So we bring this x over, we bring the 3 and the t over here on the denominator, and pretty much we get x double prime over x is equal to t prime over 3t, right? And we argue that the only possible way that a quantity that has only t in it, depends only in t, and a quantity that has only x in it, that they can be different regardless what the values of x and t that you plug in are, okay, that's the real problem there, is if they're constant, right? I mean, it's pretty much automatic that they have to be constant. I mean, think about it. Let me put it in more common language, right, so that you can see it. If somebody tells you, I have a function g of x, and I have another function f of t, and I want these two functions to be equal, no matter what x and t are. I mean, this is a ridiculous proposition, right? This cannot happen unless the two functions have no real dependence on x and t respectively, meaning they're equal functions. And that's exactly what happens here. Okay, so that's the heart of the idea of solving this problem. So you set this equal to lambda. And now the question that is being posed is, for which lambdas do we have non-zero solutions? Because remember, we said we want to satisfy the first two conditions. Obviously, the first two conditions are satisfied by the zero function. So if at the end of this whole story, you tell me that, oh, you know what, I have the zero function, I would say big deal, right? I mean, we had that zero function from the get-go. We didn't need to do all this business in order to come up with that consideration, that, or with that possibility that this is a zero function. So I want a non-zero function, and that brings us to creating the eigenvalue problem. So obviously now this branches off to two separate equations that are what? X double prime minus lambda x is equal to 0, and t prime minus 3 lambda t is equal to 0. And our starting point is going to be the second order equation. Okay, any questions so far, please? Any questions? Okay, then. So what do we do now? We're considering different cases. We're considering different cases. So the first case that we're going to consider is that lambda is greater than 0. So we have the eigenvalue problem. X double prime minus lambda x, x of 0 is equal to x of pi is equal to 0. Now, why is it true that x of 0 has to be equal to x of pi and has to be equal to 0? For a very simple reason, because u of 0 comma t being equal to 0 implies that x of 0 times t of t has to be equal to 0. And we have a very similar situation here. I mean, the only way that this can be true for any t is if the function t is 0, which we don't want, because remember we said we want to find non-zero functions, or if x of 0 is 0. And similarly, you will get that the condition u of pi comma t is equal to 0 will imply x of pi times t of t is equal to 0, which means that x of pi is equal to 0. Hence, we come up with this eigenvalue problem. We discussed now how the eigenvalue problem is different from an initial value problem that we saw in the context of our equations of the second order or any other equations. Can somebody remind us how is this eigenvalue problem different from a garden variety equal value, initial value problem? How? There are two basic differences, right? The first difference is that we don't stick to one point, right? We usually look at the endpoints of the interval. So here, our conditions involve 0 and pi. That's certainly not what we had in an initial value problem. In an initial value problem, you're looking at a specific point and you're taking the derivatives up to 1 less than the order of the problem at that particular point. This is not what you had here. Okay. The second thing is that when you have an initial value problem, anything goes as a solution. Nobody says that you have to disregard different solutions. Here, in an eigenvalue problem, we specifically want to find non-zero solutions. Okay, so we have these two very important differences between an initial value problem and an eigenvalue problem. We should not mix the two. Okay, so the eigenvalue problems are problems that are going to come up in very specific situations like the one we're looking at. An initial value problem is your garden variety problem attached to a differential equation if you happen to be looking at some specific application rather than a general situation. Okay, so the two should be clearly distinguished. Okay, and that's why the methods are completely different. And also one should say that the presence of this parameter here is pretty much what makes this whole thing so different. And now we start with the different cases. So we say, okay, so what happens if lambda is greater than 0? If lambda is greater than 0, then you have r squared minus lambda is equal to 0. That gives you two solutions. R is equal to plus or minus square root of lambda, which implies that x of x is equal to c1 e to the square root lambda x plus c2 e to the negative square root lambda x. And now you're asking, well, find this function f of x satisfies the differential equation, but for it to be non-zero, at least c1 or c2, one of the two, at least, should be non-zero, right? At least one of the two. So when you want x of 0 to be 0, that forces c1 plus c2 to be equal to 0, because that's what you get when you plug in x equals 0. When you want x of pi to be 0, that forces c1 times e to the square root of lambda times pi plus c2 e to the negative square root of lambda times pi to be equal to 0. But do you see what happens now? The first equation tells you that c1 and c2 are opposite of each other. And when I plug this into the second equation, what I get is c2 minus c2 here times e to the square root of lambda times pi plus c2 e to the negative square root of lambda times pi equal to 0. And when you factor out c2, what you get is minus c to the square root of lambda times pi plus c2 e to, I'm sorry, there's no c2 here, e to the negative square root of lambda times pi. And this number that you have here is never 0, never 0. Why is, because you have, the only way that this would be 0 is if e raised to the one exponent is equal to e raised to the other exponent. Yeah, but that's impossible. The exponential function is a one-to-one function. The one exponent is positive, the other exponent is negative. It doesn't really matter that they're opposite of each other. What matters is that one is positive, the other is negative, meaning the one number that you're going to get is greater than 1, the other number that you're going to get is less than 1. That makes the whole thing impossible. So C2 has to be equal to 0. And of course, once C2 is equal to 0, then C1 is equal to 0. And the basic premise of our search, which is that we were looking for a non-zero function, cannot be satisfied. So no positive eigenvalue. Then we look, any questions here, please? Any questions? Okay, so what are we looking for then here? We're looking for the case now lambda equals 0. That's an equally hopeless case, meaning the equation that you get is really x double prime is equal to 0, rho square is equal to 0 is the characteristic, or the, what we come to call the auxiliary equation. People do use both terms, auxiliary equation, characteristic equation. Both of these things are used in this context. And what you get is that x of x is c1x plus c2, or c1 plus c2x, doesn't matter. The order in which you set these two things is, is irrelevant here. What is relevant is that if you plug in 0, this forces C2 to be equal to 0. And once you know that C2 is equal to 0, once you plug in x of pi equals 0, you will get C1 pi has to be equal to 0, which implies that C1 has to be 0. And every hope that we would find an eigenvalue is lost right here. Okay. So then we turn to our last hope. Our last hope is lambda is less than 0. Then we get x double prime minus lambda x is equal to 0. And this gives us r squared minus lambda is equal to 0. Now, think about it. Lambda is less than 0. So when you have minus lambda, that's as if you're adding a positive number. So you have r squared plus a positive number equal to 0. It's only natural that the only solutions that you find here are complex solutions. And when you're going to express them using the square root of something, that thing will have to be a positive number. Since lambda is a negative number, it makes perfect sense that here you will have plus or minus square root of lambda times I. And this forces the solutions to be C1 cosine of square root of negative lambda times x plus C2 sine of square root of negative lambda times x. And the first condition, that x of 0 is equal to 0, implies that simply that C1 is equal to 0, right? Because cosine of 0 is 1 and sine of 0 is 0. So C1 is out of the picture. You might as well forget about this whole term, if you will. So then when you want to ensure the second condition, which is x of pi is equal to 0, then basically, now that you know that C1 is 0, what you need to ensure is that C2 sine of square root of negative lambda times pi is equal to 0. And of course, your only hope here is that this number has to be 0. And this number is 0 when whatever you plug in is a integer multiple of pi with a natural multiple of pi, I should say, natural number meaning positive integer. So minus lambda times pi should be n pi, which forces negative square root of lambda to be n, and lambda should be negative n squared. These are our eigenvalues. And what are the eigenfunctions? The eigenfunctions are going to be sine of an x, pi and pi cancel each other. And for this, the second equation, so the second equation becomes what? X prime, I'm sorry, t prime, I meant. T prime minus 3 times negative n squared, so plus 3n squared times t is equal to 0. This is a very simple separable equation, which gives what solution e to the negative 3n squared times t. So when you put everything together, you have sine of nx times e to the negative 3n squared times t. These two satisfy the two first conditions. And since the two first conditions are homogeneous, you can take any linear combination of them, in particular, put any number Cn in front of them, and that will give you the most general form for the function u of x comma t. Okay. Now remember that we wanted u of x comma 0 to be pi x minus x squared. And so what we have at hand here is that the Cn's should be chosen so that sum from n equals 1 to infinity of Cn sine of nx is equal to pi x minus x squared. And this right away forces those Cn's to be what? The Fourier coefficients of the function pi x minus x squared when you have a sine expansion. So this will be the Fourier coefficients of the sine expansion of pi x minus x squared on the interval from negative pi to pi. Notice that the function pi x minus x squared was just defined on the interval from 0 to pi. But the idea here is that since we want a sine expansion, we're going to also define it on the interval from negative pi to pi so that it becomes an odd function. Okay, so now we just want to find those coefficients and then we will be all set. Are there any questions, please, so far? Why don't we take a break to catch our breath? And when we come back, we're going to compute the Fourier coefficients. Okay. Okay, so welcome back, everyone. And are there any questions before we proceed with our Fourier analysis? Okay, let's give a slightly longer chance, see if anybody can think of something they would like to ask. Okay, then. So here I would like you to understand that our flexibility to be able to have our function initially defined over just 0 to pi. So if you want to think of this function, what it looks like, it's something like this, right? It's a parabola, right? It's centered at pi over 2 from 0 to pi. And in order to perform our Fourier analysis, we want to have it defined from negative pi to pi. But from negative pi to pi, you have any one of an infinite amount of choices as to what it should be. It could literally be anything. But what is our choice? Our choice is to choose it so that it's odd. Because once it's odd, it will have a sign expansion. No cosines are needed. And that will make it exactly equal to the sine series that we have on the left right here. And we will be able to equate the coefficients, and that will be precisely what we need. Okay? So, in other words, as we say, we extend f of x, so pi x minus x squared on negative pi to pi, so that it's odd. And now pretty much we have to compute two over pi times the integral from 0 to pi of pi x minus x squared sine of nx. That's what we need to compute. Once we compute these integrals, we're all set. Okay? So I'm going to proceed not with Euler's formula. Remember, last time when I posed the same question, there was an overwhelming preference for Euler's formula. I would like to proceed with a more traditional approach that will force us to have two integrations by parts. So, and you know what, let me show you how we don't even need to actually do that initial substitution. All those are, in some sense, steps that one could take, but one doesn't need them. I mean, they're not necessary. Everything is still doable here. So I want to think of sine of nx as a derivative, and it's a derivative of what? Of negative cosine of nx over n. If you take the derivative of this, you will see that you find sine of nx. Okay? So now we do 2 over pi times pi x minus x squared times negative cosine of nx over n from 0 to pi. And here we have something really, really cool. Plug in pi, you get 0. Plug in 0, you get also 0. So this whole thing is gone, right? That's something. Minus, and now I have to take the derivative of pi x minus x squared, and this will be pi minus 2x times negative cosine of nx over n dx. And now I have to clean up. Okay, so how do I clean up here? I have two negative signs. They become positive. I have this n. So I will have 2 over n pi times the integral from 0 to pi minus 2x times cosine of nx dx. Okay, any questions so far? Any questions so far? I mean, this is really Calc 2 and Calc 1, but you know, regardless, I would be happy to explain anything related to the first integration step that I just completed. Please understand that a second integration step will be needed here. Right? Okay, then. So let's take that second integration step. So it's pretty much the same story. So we will have 2 over n pi times the integral from 0 to pi of pi minus 2x. And now I want to think of cosine of nx as a derivative. What derivative would that be? Sine of nx over n. It's a derivative of that, dx, which will give us 2 over n pi. And I open a big parenthesis where I perform our integration by parts. Pi minus 2x times sine of nx over n from 0 to pi minus, and I will have the integral from 0 to pi of what? The derivative of pi minus 2x, which is negative 2, times sine of nx over n. And again, we're very lucky here, right? Because if you plug in 0 into sine of nx, you get 0. Sine of 0 is 0. And also, if you plug in pi, you get sine of n pi, which is also 0. So again, this whole thing is going away. And we need to, again, clean up the debris here. So you have 2 minuses, which again will give you a plus. So you will have 4 over, I have an other n now, n squared pi, excuse me, times the integral from 0 to pi of sine of nx. And here there's no need for a any other trick. The antiderivative of sine of nx is negative 1 over n cosine of nx. And I want to go from 0 to pi. And what do I get here? So first of all, there will be this negative 4 over n cubed pi, right? And then I get cosine of n pi minus cosine of 0, also known as 1. But we said before what cosine of n pi is, and I do want you to know this. I do want you to be using this properly. So it's negative 4 over n cubed pi negative 1 to the n minus 1. There is a further simplification to be made here, but let's wait to see what that is going to be. For the moment being, let's take it to be this one. And we can write down our solution, right? So we can write down that u of x comma t is going to be the sum from n equals 1 to infinity of negative 4 over n cubed pi times negative 1 to the n minus 1 sine of nx times e to the negative 3 n squared t. And that's our solution. Again, here, of course, we can be quite specific as to where the solution is valid from for x between 0 and pi and t greater than or equal to 0. And I claim that there is one more simplification step to be made here, which I would like to make it because it's kind of fun to see this. But I would also like to make one more remark on the integration by parts, because I fully understand that this is not the garden variety integration by parts that you have seen in your mathematical career so far. However, this is unavoidably the integration by parts that people do use in mathematics. So pretty much, and I can say this for the indefinite integral, you pretty much try to acknowledge one of the two factors as a derivative. Once you have done this, so you can see that in all cases, so for example, here I took the sine of nx and I acknowledged it as the derivative of negative cosine of nx. Once this has been done, then this is f of x, g of x, and then you take the prime from the one function and you put it on the other function. And of course, I want you to understand that the corresponding formula holds for the definite integral. And that's the integration by parts that you see me use every single time here, which of course is very clean, as you can see. No u's, no v's, nothing of that type, which, as I told you, nobody uses in mathematics. It's just a sort of simpler or more tangible methodology for college, for college students. But once, at some point, we have to grow out of it. Okay. And now I would like to simplify this a little. Can you see why I want to simplify it? Because this is a very, how should I put it, expensive way of saying what we're saying here. Notice that -1 to the n is either 1 or -1, right? So half of these coefficients are actually equal to 0. And we're spending too much time talking about them. So I would like, so what are the coefficients for n even or for n odd that are non-zero? Which are the ones that are for n even or for n odd? For an odd, right? For an odd. And how can you describe the odd numbers? The odd numbers are simply 2n plus 1 for n equals 0, 1, 2, and so on. So let's see how we're going to simplify this. So let me write these numbers as 2k plus 1, where k is going to run from 0 to infinity. So minus 4 over 2k plus 1 to the third times pi. And this number, -1 to the n, becomes what? Since you have an odd number, it's -1. -1 minus 1, that becomes a -2. And then you have sine of 2k plus 1 times x, and then e to the -3 2k plus 1 squared times t. And of course, this can be simplified a little more. First of all, note that k is irrelevant here. The summation that you have, the index of summation, is completely irrelevant here. So you can just simply have n again, back to n. And you will have 8 over 2n plus 1 to the third times pi sine of 2n plus 1 times x e to the -3 2n plus 1 squared t. And that's your solution. That's your solution, simplified and given in a way that is both concise and quite revealing about what is going on here. Okay. So this brings us to the end of our material. So like I said, basically, I want you to know everything that we have done up to this point very, very well. That is what's going to appear on the final exam. We're going to explain what is going to be on the final exam in a rather detailed and exhaustive way. I would like everybody to do very, very well on this exam. So please do the very last homework. And obviously, I cannot give you a quiz that has all of the work that we did today. So I will need to pretty much focus on some part of the work that we presented today and give it to you for next time. But I really want you to go over everything that we did today. It summarizes both what we had done before and it shows the next few steps. The exam is going to be not this Friday, the Friday after. That's the very last day of classes of the 8-week schedule. And it's on the syllabus. It's going to be from 8 in the morning to 10 in the morning. And is it August 4th? Let me double check to make sure. Yeah, you're absolutely right. That's August 4th. Okay. And let's take our attendance for today. What is a nice let's just focus on the fact that we just completed our material. So the keyword for today is completed. Completed for your attendance. And let me see if anybody has any questions that I could answer before we adjourn for Wednesday. On Wednesday, as I said, it's going to be our very last quiz for the semester. And then we're going to discuss some topics and also systematize our review. So I would like to actually discuss the structure of the exam right on Wednesday. So please be there, or otherwise find the recording. And there is a question regarding the second problem for tonight. So let's take a look at the second problem for tonight, see if we can give some useful hint here. I think we have actually solved this problem in class. So there's really, all you have to do is, but why? I don't understand why the second problem gives you more. It's the first problem that could possibly trouble you, because you take an odd function and you sketch it so as to be even, right? Whereas in the second case, you take an odd function, it's already odd, and you just want to find its Fourier series, and it's going to be a sine series, right? So, the coefficients here are going to be what? They're going to be 2 over pi times the integral from 0 to pi of x sine of nx dx. And obviously what we just solved is much more inclusive than this very, very simple problem. Okay? That's what you have to compute. These are the coefficients that you have to compute. Are there any more questions that I could address? Okay then. So that will be all for today. I hope you have a wonderful rest of your day. I will see you on Wednesday. And please remember that I have my office hours today at 10 minutes before noon. Okay, big one.